Welcome back to our advanced training series on two-phase fluid modeling in Flownex. I hope that the overview given in the first video laid the right foundation to get you all excited for this interesting topic. And I must say, I never get tired of working with this fascinating fluid type. So, without further ado, let's take a look at the two-phase calculation model employed in Flownex, the application of boundary values unique to two-phase flow, and then some details regarding two-phase fluid dynamics. By this time, I'm sure you have noticed that the mixing of phases in Flownex are handled in a homogeneous manner. This approach is called the homogeneous equilibrium model. It means that there are no differentiation made in location of individual phases during flow. So the saturated liquid and vapor phases are homogeneously distributed or mixed. It also implies that the thermophysical properties are expressed as single values in weighted average combination, as discussed in our first video. It is furthermore important to note that mass, momentum and energy transfer between the phases are not taken into account. But the various boiling and condensation regimes are all accounted for by their own unique empirical correlations for both friction factor and heat transfer calculations. And lastly, Flownex also incorporates critical flow models for critical velocities and mass flux calculations, or choking, as it is more generally known. The homogeneous equilibrium model reduces calculation complexity, it speeds up solution time, and is conceptually more user-friendly. But its accuracy does, however, decline somewhat for complex flow patterns, countercurrent phase flows, upright flows, and rapid acceleration and pressure changes. All in all, however, this is definitely the best model for systems level calculations. Next up, let's discuss a few tips on boundary values applicable specifically to two-phase fluids. We'll start off with a quick summary on single-phase fluid boundary values. It might even be a good idea to quickly look through the basic training video on boundary values again at this stage. The combination options in specifying the boundary fluid conditions for single-phase fluids are pressure and temperature and then either pressure or mass source, and then mass source and temperature. Remember that the interrelation between pressure and mass flow, that is delta P equals half mass flow squared divided by density area squared, gives that only one or the other can be specified on a boundary to avoid overspecification. When adding a boundary value for temperature within my network, an energy source will be enforced on that node. When adding a mass source or pressure boundary value within the network, a mass source will be enforced on that node. Do you guys still remember these principles? Alright then. For two-phase flows, we'll have to quickly look at the fluid property diagrams to visualize the possible combinations of fluid properties. By looking at the temperature entropy diagram, obviously, if I have the temperature and entropy, I'll be able to obtain the matching pressure line and quality within the mixed phase region, and from there I can calculate all other fluid properties. But since entropy is not a frequently used variable, Flownex rather allows for specification of temperature and pressure, from which the entropy and then all other properties can be deduced. Remember that within the mixed phase region, the pressure line is completely flat. So I'll have to specify the quality to indicate the required position on the temperature entropy diagram. In terms of the pressure enthalpy diagram, specification of the pressure and enthalpy will give a precise position on the diagram, but within the mixed phase region you can also specify the quality and enthalpy, or quality and pressure, to indicate a precise position. Having obtained this, all other fluid properties like temperature, density, etc. can then be calculated. So, for a two-phase fluid, The boundary value combination options for pressure are either temperature, enthalpy, or quality. In combination with temperature, you can specify either pressure, quality, or mass source. For combinations with quality in the mixed phase region, you can specify either pressure or temperature. Combinations with enthalpy include either pressure or mass source, and when specifying mass source, you can also specify combinations of either temperature or enthalpy. When adding a boundary value for temperature, enthalpy, or quality within my network, an energy source will be enforced on that node. When adding a mass source or pressure boundary value within the network, a mass source will be enforced on that node, similar to the single phase fluids. Just note here again the statement that a boundary value for quality within my network will enforce an energy source on that position. However, within a two-phase tank that has a volume, the quality specification only acts to determine the liquid level as explained in our first video. So, if my balanced mixture quality within the tank has any value between 0 and 1 during steady state calculations, no energy source will be created on that tank. Think about this principle for a while and play around with the values of the first exercise to investigate this effect. It is very important to have a thorough understanding of its implications. Fluid dynamics also have its own set of challenges for mixed phase flow. To calculate pressure loss, Flownex employs the Lockhart-Martinelli method, which uses a combination of the pressure loss for only saturated liquid and only saturated vapor. The momentum conservation equation is also a little bit more complicated than that of pure liquid or gas. But it is important to note that we handle two-phase fluids in a uniquely detailed manner in Flownex. Pressure loss with two-phase fluids can however sometimes be counterintuitive. To illustrate this, I'd like you to try the following exercise. A 100 mm diameter pipe of 50 meters with a roughness of 0.07 millimeters is connected with a sharp type entry. That just means that the secondary loss factor is 0.5 to a 10 cubic meters pressure vessel at 5 MPa. For 15 kilograms per second of two-phase water flowing through the pipe, determine the pressure at the pipe outlet when the conditions in the upstream reservoir are firstly saturated liquid, then secondly a steam quality of 0.5, and thirdly saturated vapor. Then, using the same network, investigate the following scenarios. In the case of saturated liquid in the upstream reservoir, does the pressure loss lead to two-phase flow or to subcooled flow? In the case of saturated vapor in the upstream reservoir, does the pressure loss lead to two-phase flow conditions or superheated flow conditions? And then, do these findings confirm your expectations? As with the first exercise, we'll discuss the answers in a separate follow-up session. While performing this exercise, I would suggest a few general tips for mixed phase flow modeling. I usually start off by changing the pressure relaxation parameter to 0.5 to account for the large density changes that is to come. Also, it is better to have two pressure boundary values than using a mass source boundary value. This aids convergence by setting the pressure limits from which densities and thereby the related mass flow is calculated. And it allows choking to be freely incorporated. Make sure that you have assigned enough increments to the pipe to ensure grid independence, and confirm that the convergence accuracy is sufficient for the model's purposes. Convergence with a mass source boundary value can however still be obtained by significantly reducing the relaxation values in the solver settings and increasing the allowed iterations. This does, however, require understanding of the relaxation approach, and it will take more solving time. And while we are on the topic of challenges with regard to convergence, conditions where two-phase fluid properties undergo steep changes with reference to another property oftentimes require more iterations to converge, and may even require relaxation of solid parameters. These conditions, for example, include transition from liquid phase to mixed phase due to the steep change in density, as you will experience in this exercise. Then also conditions close to the critical point where large changes in densities occur. Flow conditions close to the choking point, which is the maximum attainable gas flow through a given flow area, since there is a discontinuity in pressure flow relations at that point. And then lastly, buoyancy driven flow, which will be discussed in more detail in our next video on two-phase fluid modeling. And that's it for now. Be sure to tune in for our next video in this advanced training series. And until then, have a wonderful time.